Assalamu alaikum everybody to this video lecture of electromagnetic waves at Yildirim Bayezid University course EE304. I would like to welcome everybody to this video lecture. Before we start, I would like to wish you all safe from this coronavirus disease, you and your family, and I would like to remind myself and you to follow the recommendation and the instructions to protect ourselves, our family, our community from the spread of this disease. Today we'll be talking about a new lecture. The lecture will be divided into 3 separate videos, and I will send the details over the USEM system. The first part, which is this part, will be talking about the magnetic boundary condition. As we know, the boundary conditions means the rules that are governing the field at the interface or at the boundary between 2 different media. Here we are talking about magnetic field boundary conditions, which means the 2 media, media 1 and media 2, are different in their magnetic properties. So media 1, as shown here, is media with permeability mu1, media 2 does have a different permeability mu2, and we would like to study the relationship between the fields, the magnetic field in media 1 and magnetic field in media 2. To do this, and in a similar way to what we did with electrostatic field, we'll consider the 2 different components of the magnetic field. The normal component, which is a component parallel to the direction normal to the interface, and the transverse component, which is a component that is parallel to the interface or parallel to the boundary. So let us start by the normal component, and in order to come up with the rule regarding this, we're gonna construct a very short cylinder. And this cylinder, the height is very short, the axis is parallel to the perpendicular to the interface, and of course, also the surface area or the base of this cylinder is a very small one. Because this cylinder is very short and it's normal to the boundary, we have no flux, no magnetic flux going from the side because it's very short. And then all the magnetic flux is going normal to those bases, the base in medium 1 and the base in medium 2. Applying Gauss's law for magnetic flux, which is B dot ds over a closed surface equals 0. To remind you, a closed surface means that a surface that is surrounding some volume, like a cylinder, like a cube, like a rectangular parallelogram, something that is enclosing a volume. The total flux, magnetic flux out of a closed surface equals 0. We call this relationship the conservation of the magnetic flux, and from this one we concluded 2 facts about the magnetic fields. Number 1, the magnetic field lines are closed lines. That's why the number of lines going out of the surface equals the number of lines coming into the surface. So the net is 0. The second property that we learned from this rule is that we have, always, dipoles of magnetic sources. There is no separate magnetic source. The magnetic source always exists in pairs, north pole and south pole. So applying this B dot ds, as we said, we have 3 surfaces, as we said before, the top, the bottom, and the side. The height of the cylinder is very small, so the side surface is negligible, and we only have the flux out of the base or the bottom side and the flux out of the top side. The flux out of top side, which is in medium 1, equal the normal component of the magnetic field multiplied by the area of the top base of the cylinder or the top surface of the cylinder. And here B dot ds, as we also said before, this surface is a vector quantity and it is pointing out of the surface, so it is pointing out. So it's normal component of field in medium 1 multiplied by the delta S in this direction. For the other surface, the surface at the bottom, we have the field also going in, so there is a difference inside. ds for the bottom surface is going out of the surface, out of the volume. It is going to the down direction, while we are considering this component to be the direction of normal component. So we have normal component of field in medium 1 multiplied by the surface area of the base of the cylinder in medium 1 minus the component of normal field in medium 2 multiplied by the surface area of the base of the cylinder, and this equals 0. From this we can easily conclude that the normal component of field 1 equals the normal component of field 2, which is the continuity of normal component of magnetic flux density. So B normal 1 equal B normal 2, and this is in all cases. The second component of the field is the tangential component, which is a component that is propagating or directed in parallel to the interface. In order to conclude the relationship between the tangential component of field in medium 1 and tangential component in field in medium 2, we are applying Ampere's law. Ampere's law is stating that H dot dl over any closed contour equals the total current enclosed. So consider this contour, which is a very small rectangle. The height here is very small, and we have delta L length parallel to the boundary. So according to Ampere's law, H dot dl, so H integrated across the path that I'm drawing here, equal the total current enclosed. So also this is applying the right hand rule. So this might look like, it is following the right hand rule. So we have the field propagated this way, so the current is going in. So now applying Ampere's law on this setup, we have the contour does have 4 sides: top side, right, bottom side, left side. Those left and right sides are very short, so we can easily neglect. The effect on this integration is only coming from the top side, which is the parallel part of the contour to the boundary, and the bottom parallel part of the contour to the boundary. This one here, H dot dl, is H1 tangential multiplied by delta L. This one is H2 tangential multiplied by delta L. If we consider this is the direction of the tangential component, for the upper side, H dot dl will be positive. For the bottom side, H dot dl will be negative. That's why we have H tangential 1 multiplied by delta L minus. This minus is because delta L is in this direction, while we assumed H tangential 2 is in the opposite direction. That's why we have this negative sign. So now we have H dot dl on the left side, which is this expression. On the right hand side, we have the current I. So the current I is the total current enclosed by this contour, and in this contour there is no source of current except for a surface current. If we have a surface current K, then the right hand side will equal K multiplied by delta L. And we need to pay attention here to the direction. So using the right hand side rule, if we are rotating in this direction, the current is flowing inside this like screen. So we have here H tangential 1 minus H tangential 2 equal K. So the difference between the tangential component of the field H equal the surface current density. We can write it this way: H1 minus H2 cross product AN12 equal K. And we need to pay attention to the direction. AN12 is from the normal component from medium 1 to medium 2, which is this component. So we can write it this way: H1 minus H2 equal cross product AN12 equal K, or H tangential 1 minus H tangential 2 equal AN12 cross product K. So this is the second part of the boundary condition on the magnetic field that is related to the tangential component. Now it is time to apply our learning on this example. So on this example, we have like two magnetic materials that are different from each other. Material 1 with mu1, material 2 with mu2, and we have a magnetic field H1 that is known on medium 1, and this field is making an angle alpha 1 to the normal to the boundary. What is required is to find the magnetic field H2 in medium 2, magnitude and direction, which means we need to find the value of H2, the magnitude, and its direction, or the angle alpha 2 that the field in medium 2 is making with the boundary, with the normal to the interface. So now I would like you to pause this video and try out solving this problem yourself. Give yourself the time. You can go back to the previous slides and see the boundary conditions. The boundary condition on normal component, B normal 1 equal B normal 2. The boundary condition on tangential component, which is H1 tangential minus H tangential 2 equal K, which is the surface current. In this problem, we have zero surface current. So please pause the video now and try to solve this example yourself. This is the best way to learn and apply correctly. I'm assuming now you are back from the pause, and let us solve this example together. First, we're going to write the two boundary conditions. As I said, we don't have surface current, so H tangential 1 equal H tangential 2, and B normal 1 equal B normal 2. So now we need to find H tangential 1 and H tangential 2. Here, this is H, so we are expecting, or like when we do the decomposition, H tangential will be in that direction, and H normal will be in that direction. So the normal component will be multiplied by cosine alpha 1, the tangential component will be multiplied by sine alpha 1. So H tangential 1 is H1 sine alpha 1. Similar thing we do for H2, it will be decomposed into two components, tangential component in that direction, and normal component in z direction. The normal component is cosine alpha 2. The tangential component is sine alpha 2. So we have from the first boundary condition h1 sine alpha 1 equal h2 sine alpha 2. For the normal component, we have b normal 1. So we have for the normal component b normal 1 equal b normal 2. The normal component for b equal mu1 h normal 1. H normal 1, as we said, is h1 cosine alpha 1. So we have this relation for the normal component. Now, as we solved this problem like a couple of times before, we divide equation 1 by equation 2. So we'll have sine alpha 1 divided by mu1 cosine alpha 1 equal sine alpha 2 divided by mu2 cosine alpha 2. Sine over cosine equal tan, and the m2 at the bottom will go to the left side, m1 at the bottom will go to the right side, and we'll have this equation. In this equation, alpha 1 is known, mu2 is known, mu1 is known. The only unknown here in this equation is alpha 2, so we can find alpha 2. Once we have alpha 2, we can substitute in any of those two equations. This equation is easier. Now alpha 2 is known, h1 is known, alpha 1 is known, so the left side is known, sine alpha 2 is known, so we can find h2. So now we have the value for h2, and we have the value for alpha 2, and we have the problem solved. So we now have the solution for alpha 2 and h2. Just like a quick comment on this, if we have mu2, like for example like a ferromagnetic material with mu2 much larger than mu1, then we'll have alpha 2 like very close to normal. So if mu2 is very large compared to mu1, we'll have this angle like 90, which makes the surface, the h2, traveling parallel to the surface. On the other side, if mu1 is much larger than mu2, then alpha 2 will equal 0 and will go normal out of mu1. So if mu2 is ferromagnetic, h2 will be like surface field. If mu1 is ferromagnetic and mu2 is normal or non-magnetic material, the h2 will be normal to the boundary. Of course, like you can verify this by substituting the number and calculating the value for alpha 2. Another example. Here, this example, we are given a magnetic flux density B1, which is in Cartesian coordinate system with component in X, component in Y, and a component in Z, with the unit of the magnetic field millitesla. We have the value for mu1, we have the value for mu2, and in this case we have a surface current. Of course, the surface current unit is ampere per meter, and its direction is in the AX direction, and we would like to find B2. Of course, B2 is a vector quantity, and this vector quantity, finding it means that we find the magnitude and direction of B2. Again, for this example, I would like you to pause this video and to try solving this example yourself. The steps should be like clear in your mind. We need to write the boundary condition. The boundary conditions are one related to the tangential, one related to the normal component. and we need to first define what is normal and what is tangential. The two media are separated by like xy plane. So we have like an xy plane is our boundary. So the normal component is the z component, the tangential component is the xy component. So I give you like enough hints. Please pause the video, try to solve this example yourself, then come back to the video. Okay, hope that you solved this example yourself, and now let us see how we will solve this. So we'll work first with the normal component. As I said, the normal component is a component that is in the z direction. So it's just like the z component, or you multiply the field, the total field, dot product, the normal component, and so this is like a more generic solution. We can just say the normal component is the z component, but to be formal, like here it is. Like to find the normal component is the dot product of the field with the normal unit vector in the direction of the normal unit vector, which is the z component. We know that the boundary condition is b normal 2 equal b normal 1, so we found the first part of b2, which is the normal component in the az direction. Now let us work with the tangential component. Tangential 1 equal b1 minus b1 normal, or we can say it is the xy component of b normal 1, but this way is more general function if an12 is not parallel to one of the unit vectors. So this is the b tangential 1. The boundary conditions that we have is related to h tangential 1. We can find it easily by dividing b tangential 1 by mu1, and it will have this expression. Now we can apply the boundary condition h tangential 2 equal h tangential 1 minus an12 cross product k. H tangential 1 is this expression. The an12 is minus z. Why? Because it is the vector that's coming from medium 1 to medium 2. Medium 1 is, as shown here, is the upper medium. Medium 2 is the lower medium. So the vector that's coming from medium 1 to medium 2 is coming from positive to negative. So it is in the direction of negative az, cross product with the k unit vector, the k surface current. We do the math to find b tangential 2, which has this 2 component. So now the total field is just like summing b normal 2 and b tangential 2, and we found out the total field in medium number 2. This will be the end of this video, which is the first part of lecture 5. See you in next sections.